Okay. Just a moment. Okay. So last week we introduced some additional properties about the soils, including the modulus of the subgrid reaction and the definition of the resilient modulus. The resilient modulus is one of the most important features we have to estimate for the materials, the aggregate materials for the design of the pavement. And the resilient modulus is very similar to the modulus of elasticity for one material, but they have some difference. Basically, the modulus of elasticity is the property of one material, and it cannot be changed based on the external conditions. But the resilient modulus is changing with respect to the moisture levels, the loadings applied to the materials, and so on. So it's an empirical feature instead of the physical feature. Basically, we have to use the resilient modulus test to measure the value of the resilient modulus for one material, the subgrade or the granular-based materials. And to do this experiment, we need to prepare the sample. Usually, we need to prepare the cylinders for the sample, and then we will have some repeated load applied to the sample. And with this kind of load, we will find out the relationship between the stress and also the normal stress and the strain. And by the repeated load, you will find out that the stress and the strain will be recovered during the for a lot of cycles, depending on the condition we set in the resilient modulus. And we're gonna need to use the property of this cycle. So they say that this is one typical cycle we will observe from the resilient modulus test. And by finding out the maximum and minimum value of the stress and strain, and also their differences, we can then, using their slope, to identify the resilient modulus. Basically, in this equation, sigma d would be the deviator stress, and epsilon d will be the recoverable strain. And we need to find out these two values from the resilient modular test, or we say that the MR test. And this is the instrument we're going to use for the resilient modulus test. Usually we have to use the this is called the triaxial loading machine. And in this machine, you will have a set of the components, and you can actually find out the what's the purpose of each component in the lab instruction. And I will not go through the details about each one. Basically, in the experiment, we will have the air filter. We will have air filter in the cylinder, the crystal cylinder, and then it will create an air pressure around the sample. And then we will have the repeated load applied to the sample. And based on the stress and the strain we measured from the sample, we can then find out the resilient modulus. So that's a very brief introduction about the process of the MR test, and of course you need to read through the AASHTO test 307, which would be the materials I shared in the lab instruction. You have to read through this instruction to see what's the details about this experiment. And during the experiment, you will set up, at each scenario, you will set up one contact pressure, or we say that the cell pressure, which would be the pressure of the air applied to the crystal cylinder. And then we will have the repeated load. So here, with this figure, you can find out some typical load. The load will be very short. It will only last for less than 0.5 seconds. In this case, it will be less than 0.1 seconds. And the load is applied and then released. With that, we can reproduce the load applied to the pavement in reality, which is caused by the repeated traffic load to the road. And once with the data collected by the MR test, you can then find out the relationship, draw the figures between the deviator stress, which would be the stress loaded by the machine, and the axial strain, that is the strain estimated through the displacement during the experiment. And as you have the repeated load, so you will find out the recoverable strain, which would be multiple circles during the experiment. And then with these circles, you need to find out the what's the value of the sigma d, that will be the deviator stress, and what's the value of the epsilon d, that will be the recoverable strain. And you need to find out the slope from the maximum of the line to connect the maximum and the minimum values. And that's how you will calculate the resilient modulus from each experiment. And of course, also in this figure, you can find out another value, which is called the sigma first. And this one is actually the contact pressure. That is also the pressure from the air. And this table actually shows the process data from the experiment. You basically in the experiment, you will conduct a lot of sequence of the to apply the load, and for each sequence, you will find out the maximum stress and minimum stress, and also this would be the stress applied from the experiment. And what you will do that you will try to find out the values. This would be the values from the data you're going to collect it from the machine. So you have the actual measured maximum stress, the contact stress, the cyclic stress, resilient strain, which is also the sigma epsilon d, and the resilient modulus. The resilient modulus is actually calculated based on the cyclic stress and the resilient strain. So in this table, the cyclic stress is actually the deviator stress. It just apply different terms to represent the same value. And the resilient strain is epsilon d. With that, the MR will be sigma d divided by epsilon d. That's the way for you to find out the resilient modulus. Also, you might be worried about how you can find out the cyclic stress. Basically, the cyclic stress will be the difference between the maximum stress and the contact stress. So the contact stress, which is also the sigma first, and the maximum stress, usually we define this one as the bulk stress. That is the highest stress we will observe from the No, not the bug stress. That's the direct maximum stress applied at the top of the specimen. So this would be the stress and stress applied to the sample in the MR test. So we have the for the test we have the contact pressure, which is the sigma first, and as you in the experiment we have the air filled in the cylinder so that the contact pressure is applied to both top and the side areas of the specimen. So what we will observe is like we have sigma first actually equals to sigma 3. Sigma 3 is the pressure applied to the side of the cylinder. And we also have the definitions about the box stress. The box stress represents the stress, the total stress applied to the sample, which will be the stress applied from all directions of the sample. So the box stress theta will be sigma 1 plus 2 times sigma 3, which would be the stress applied at the top plus the stress applied at two sides of the specimen. That would be sigma 3 at the sides. And we also can define the mean stress, which is P, which will be P will equal to 1/3 of the box stress. And the deviator stress, the definition of the deviator stress is related to the maximum stress. That would be the largest stress applied to the sample, sigma 1. Of course, if you here you can see that sigma 1 equal to sigma d plus sigma first in this figure. So the deviator stress will just be sigma 1 minus sigma 3. So if you put all this equation together, you can find that the box stress theta equal to sigma d plus 3 times sigma 3. That would be the sigma 3 would be the contact pressure or the side stress. So that's the stress applied to the sample during the MR test. And the next thing we need to do is like how we're gonna analyze the data and how we're gonna present the test results. So basically, for each contact pressure and each type of the load we applied, we can find out one value of the resilient modulus. And of course, we also work on the different moisture contents. So in the experiment, we will apply different values of the load to the sample, and the load will be represented as the box stress. If you combine the deviator stress with the contact pressure, you can calculate the box stress. That is a theta. And at every experiment, we need to check different contact pressure. The contact pressure is set as 3 psi, 5 psi, 10 psi, 15, and 20 psi. You also need to conduct this number of the experiment in your test. And for each box stress and each contact pressure, you can calculate one resilient modulus. And then you need to find out a line to fit to these data points. And this figure shows the result which will fit to this the line which will fit to those test results. Basically, you can find that the resilient modulus is a function of the box stress. So with the higher load to the sample, the resilient modulus would be larger. And this is one typical expression about the relationship between the bulk stress and the resilient modulus. For this specific sample, LM4 with the moisture level of 4%, the resilient modulus MR equal to 16.3 times theta to the power of 0.55. So this is the one sample, LM4. We can also find out the relationship between the resilient modulus and the deviator stress. If you draw the figure about the resilient modulus with respect to the deviator stress, you can find that they are not fit to the line very well. But instead, if we consider the result for each contact pressure, you can see that the for those points will be almost along a line or along the curve. So we can then further define or develop a new model to describe the relationship between the resilient modulus and the deviator stress. And here we also need to think about the bulk stress. So with that, we can actually develop a new model. So MR would be in a function of theta and sigma d. And for this sample, we have MR equal to 6.19 times theta to the power of 0.74 times sigma d to the power minus 0.078. So this would be the relationship you have to calibrate or you have to estimate based on the data you collect from the experiment. You need to find out the parameters for the first model and also the parameters for the second model. And of course, with different samples you prepared, you can find out the different values. Like for the first one, the coefficients will not be 16.3 or 0.55, and it also applies for the second model. And so that's the way for you to show the result to based on the data points you collect from the experiment. And we can also find that based on the experiment, we know the resilient modulus is in a function of a set of the parameters. It could be in the parameter of the bulk stress. It could be, well, if it's bulk stress, obviously it's also the mean stress. And it can also be in the function of the octahedral stress. It can be the function of the density, moisture contents, and so on. Those are all being calibrated in the literature. So a lot of researchers have conducted experiments about the relationship between MR and a set of the variables. Basically, if we increase the bulk stress, which would be the load applied to the sample, or we increase the density, then we can find the value of MR would be larger. MR would be larger. And this indicates that the pavement or the materials is stiffer, so we have a stiffening effect. And if we increase the shear stress or we increase the moisture contents, then the MR value will be smaller and the aggregates will be softer. So that's the two opposite effects from the parameters that can affect the values of the MR. Typically, we can make a summary about the factors with respect to the resilient modulus. Those are actually the result we obtained from the past study. If we increase the bulk stress theta, we will have a significant increase about the resilient modulus. And of course, if we increase the shear stress, the resilient modulus value will be decreased dramatically. And also, if we make the grid of the particles larger, we can slightly increase the resilient modulus. This is just a minor effect. And of course, for the fine particles, it will reduce the value of MR. The size of, with larger size of the particles, the resilient modulus value will be larger. If we increase the density of the aggregates, the MR value would also be larger. And the last one, for the moisture contents, it also has a very significant impact to the resilient modulus. And by increasing the moisture contents, we can observe the very obvious reduction in the resilient modulus. So that's the factors, the common factors which will affect the values of the resilient modulus. And we actually have, in the previous slides, we actually showed some two typical models. One is about the relationship between MR and the bulk stress. The other one is the relationship between MR and bulk stress and the deviator stress. Actually, we have some other models to describe the relationship. There will be three common models applied for the relationship between the bulk stress, deviator stress, and the octahedral stress. And here, the octahedral stress is defined as one moment of the deviator stress, and the tau octahedral stress would be the square root of 2 times sigma d divided by 3. And the first model you probably will use is the k theta model. So here we assume that MR equals to K1 times PA times theta divided by PA to the power of K2. So here PA is a coefficient, and the value is 1 kilopascal. Once you have the model, the data points about the resilient modulus and the bulk stress, you need to estimate the value of K1 and K2. So that's the first model. The second model is called the Uzen model. And in this model, we have to consider both the impact of the bulk stress and deviator stress. So that will be theta and sigma d. And we will have the relationship as K1 times PA times theta divided by PA to the power of K2 times sigma d divided by P2 PA to the power of K3. And in this model, you need to estimate K1, K2, and K3. Another model that is commonly applied is called the REGRESSION model. So in the REGRESSION model, instead of applying the deviator stress, they use the octahedral stress, which is one equivalent value of the deviator stress. So they have the value of K1 times PA times theta divided by PA to the power of K2 times tau octahedral divided by PA plus 1 to the power of K3. So in this model, you similar to the previous one, you need to estimate the coefficient K1, K2, and K3. And so now I have a question for you. So we have several models. We have two models applied here. What do you think? What's the model of this one? Do you have any ideas about it? Do you know what's the model of this one?
It has to be the K theta model, the first one.
Yes, so this is the K theta model. It's basically the same format. It only assumes that the resilient modulus is the function of bulk stress. And what about the second one? So if we go back to check the formula, it will be very similar to the Uzen model. And the in user model, you assume that MR equal to K1 times PA and theta divided by PA, K2, and sigma D divided by PA, K3. So here, PA, all the constant is a 1 kilopascal, and the coefficient is a K1, K2, and K3. So K1 is a 6.19, K2 is a 0.74, and K3 is a minus 0.078. So these are the two models you have to calibrate based on the data you obtained from the experiment. And in your lab report, you also need to find out those parameters, those data points, and then calibrate these two models, the K-theta model and the UGEN model. Of course, if you are considering the if you do multiple tests about different moisture contents, then you can make a different model or calibrate different parameters with under different moisture contents. And or you can choose the AASHTO model. Either way is fine. UGEN or AASHTO model. Either way is good for the lab report. So that's the analysis about the data you collect from the resilient modulus from the resilient modulus test. And the next thing I want you to know is about the effect of the water contents on MR values. As I described previously, the water contents has a significant impact on the MR values. By increasing the moisture contents, the value of the resilient modulus could be reduced significantly. But that actually depends on the types of the materials. For example, if we consider two different aggregates, granule A and granule B, basically granule A has larger particles and granule B will be finer. If we go to check the result between the resilient modulus and the bulk stress, you can see that for the granule A material, under different moisture contents, we have three different values of the moisture contents. 3.7%, that will be the blue points, and the 5.53%, that will be the this would be the 5.5%, and the triangle would be the 3%, and the square would be the 7%. The values of the resilient modulus will be very close to each other under the same bulk stress. So this means that for the granule A materials, the MR values is not sensitive to the water contents. But if we go to check the granule B materials, still we have three different water contents applied. We have the value of 4%, 5.9%, and 8%. And you can see that the value of the resilient modulus will be very different under different moisture contents. And this one indicates that the resilient modulus is very sensitive to the water contents, and also is highly related to the percentage of the fine particles in the fine particles in the aggregates. And usually with the higher values of the fine particles, the resilient modulus will be smaller, but it's still depending on the structure or the grain size distribution of the aggregates. So that's the impact of the moisture contents. We also have some typical values about the resilient modulus measured for different types of the soils. For the soils defined by the AASHTO method, we have A1 to A7. Basically, with for the with lower group index, you can find out larger values about the resilient modulus. For A1A, the typical values of the MR will be 276 megapascal. But if we go to see the A7, it's reduced to some value less than or around 50 kilopascal. So this indicates that the material is softer and it may be weak to support the traffic load. And the next one is this table actually shows the typical values of MR under different soils defined by the USCS method. With the USCS method, depending on the percentage of the gravel and sand particles, you can find out different values of the MR. And for the well-graded gravel, you can find out the very large resilient modulus. The value is around 283 megapascal. But if you have some clay or some clay materials, the value would be very small, and it will be less than 100 or even close to 50 megapascal. And this one is very important for you to determine what the thickness of each layer you have to apply if you select one specific soil for the subgrades or for the base and subbase layer. So that's the basic fundamental introduction about the resilient modulus test and the data analysis. Also, there will be one Excel sheet I will share with you on Emily to learn after this class. So this is the one template for you to process the data that you collect from the experiment. Basically, in the experiment, you will collect the data. You will have the data like the which will be collected in this sheet. The 3 psi, 5 psi, 10 psi, 15 psi, and 20 psi. You will have the displacement and load information. And then you need to do some adjustment about displacement because at the beginning the machine may not be aligned very well, so there will be some adjustment you have to make. And after that, you need to find out the maximum load and the minimum load, which is applied for you to determine the maximum and minimum stress. And also you need to identify the maximum and minimum strain, and is applied for you to determine the resilient strain. And this for each scenario, 3 psi, 5 psi, 10 psi, you need to find out this maximum and minimum values. And then this value will be automatically assigned to the to this sheet, the auto create sheet, and it will show the result from each sequence under different load. So we have the sequence number and different and for each sequence you have different values like the 3 psi, 5 psi, 10 psi, and 15, 20 psi. So this sheet is generated automatically, and once you have data loaded to this sheet, it will also automatically generate a summary file. It will give you the summary, clean the data from the auto-created sheet, and then summarize find out all the necessary data points you need to use for the final analysis or for the generation of the figures. And you will then need another Excel sheet. Which will be the template 2, and the template 2 will try to collect all the information from the previous sheet. This would be the one from the summary sheet in the template 1, and this raw data will then be further summarized into this simple table, and it will show you the sequence number with respect to the maximum stress, the contact stress, and also you calculate the cyclic stress. And you also need to use the displacement that you, or the strain that you calculated from the previous, from this sheet, to find out the resilient modulus. Maybe this one is better. Find out the resilient modulus, and then you have to draw the figure. This figure actually comes from the box stress, that will be maximum stress, and the resilient modulus. And this figure shows the relationship between the deviator stress and resilient modulus, which would be the cyclic stress and the resilient modulus. And you need to use the command in the Excel to find out the parameters or find out the curves to fit to those lines. And for this specific example, we have the k-theta model between the relationship to find out the relationship between resilient modulus and box stress. And also you need to find another model to describe the relationship between the resilient modulus and deviator stress. So that's the data, the part about the data analysis you need to do for the MR test. Do you have any questions so far about this test? You can raise your hand or you can leave the message in the meeting chat. Okay, if we don't have any questions, then we still have 8 minutes left. I will give you a very brief introduction about the CBR test, which will be the materials in Node 5. And the CBR test is, which is also called the California bearing ratio test. It's also an empirical features of the soil. So as you can see here, we have found out the coefficient of the reaction. Basically Poisson's ratio is the physical features of one material. We also have MR test to find out the resilient modulus. We have linear models and nonlinear models to find out the relationship between the MR and the deviator stress and the box stress. And the next feature we want to measure is the California bearing ratio, the CBR. And usually the CBR is applied to measure the soil's strength or ductility, ductility and the moisture susceptibility characters. It shows how the material is sensitive to the load and the moisture levels. And usually the California bearing ratio is calculated based on the comparison to a standard material. Usually we're going to choose the standard crushed rock base. And in the figure here shows the test of the CBR, and you will see that we will first need to prepare a sample about the soil, and then we need to apply contact pressure, which would be some load, some weight applied on top of the sample, and then we will need to apply the load to the surface of the soil, and we will then increase the load, and as the load increased, we will see there's certain penetration to the soil sample, and we're going to measure the penetration with respect to the load applied to the sample. And the CBR, which is the California bearing ratio, is calculated as a load carried by the specimen at 2.5 millimeter penetration, which is also 0.1 inch penetration, divided by the load carried by the standard crushed rock base. And usually that will be the load, the unit load at 0.1 inch in PSI divided by 1000 PSI times 100, which will show you the percentage. Or if you are using the unit of the kilopascal, the value at the bottom would be 6900 kilopascal. So you can see that the most important part for the CBR test is to find out the load at the penetration rate of 0.1 inch or 2.5 millimeters. And so with that, we just need to record all the penetration values and the load applied to the specimen. So this figure actually shows the value from the all the typical curves about the load and the penetration value. So the red line is the standard relationship between the load and the penetration, and the blue line is the test value for the sample. Basically, usually at most of the case, the line of the specimen will be lower than the standard, which means that the CBR value should be between 0 and 100. And for the as what we specified previously, the unit load should be selected at the value with the penetration of 0.1 inch. So we need to choose the value at 0.1 inch, and this 1000 psi would be the standard aggregate, and this one would be the value for the sample that you are trying to measure. Usually for the granule base, we must have the CBR value larger than 80%. For the sub base, we need to make sure that the CBR is larger than 20. And if we have the clean gravel, then it would be very hard for us to do the compact. So usually we do not do the measurement for that materials. So that's the basic steps for you to conduct the CBR experiment, and the way for you to estimate the California bearing rate. So this page summarize the CBR test. First, you need to prepare the sample and provide the appropriate compaction to the sample so that we can achieve the certain density of the specimen. And then for the CBR test, usually we will conduct two experiments. One is the regular experiment, or we call the unsoaking experiment. So we just add some water to the aggregates and then do the experiment and estimate the moisture contents. The other one is about the soaking experiment. In that experiment, you have to prepare the sample and soak your sample in the water for 4 days, and checking the swelling of the soaking sample, and also do the experiment and check the CBR values for the soaking sample. And once you have the sample prepared, you need to put the sample in the loading machine and apply 4.5 kilogram surcharge to represent the load from the upper layers. And then you will have the 50 millimeter piston, which will apply some load to the surface to the specimen, and this piston will be forced to penetrate the specimen with the certain loads at a constant rate. Usually the rate is set as 1.25 millimeter per minute. So usually you will find out the value of the 2.5 millimeter inch or 2.5 millimeter penetration after 2 or 3 minutes. And then you have to record the load applied at the penetration value of 2.5 millimeters to calculate the CBR value. So that's the summary about test procedure. In the lab instructions, you have more detailed information about how to conduct the experiment, and our TAs and the lab technicians will give you more information in the lab, and you can follow their instructions to conduct the experiment. I guess that'll be all about the lecture today. Do you have any questions? If you don't have any questions, then that will probably be all about the lecture today. And again, as we're gonna start our first lab tomorrow, so I strongly encourage you to watch the video and read the course the lab instructions. And if possible, it's better for you to print out the lab instructions and bring it to the lab so that you can always check the steps and avoid any potential mistakes that you're going to operate in the lab. Okay, if there's any other questions, I will close the meeting today, and just feel free to send me email if you have any question. And I hope we can enjoy the lab experiment. Okay. Hey, thank you very much for your time, and I will see you on Wednesday.